We will next look into another microprocessor, which is an advanced version of 8085, which is known as 8086 microprocessor. So, like 8085, I said that this is one of the basic microprocessors that we have, and for understanding any microprocessor architecture, microprocessor microcontroller architecture, it is better to start with 8085. But nowadays most of the systems that you see are based on some advanced microprocessors. Again, those advanced microprocessors are quite complex in nature. So, we will try to see how this evolution has taken place from 8085 towards the next higher level microprocessors, and 8086 is the next step. And from this 8086, the architecture remained more or less, the theme remained same, only the features have got modified, in the sense that the memory structure, then the registers that we generally have, their organization. So, those things remain unaltered. Only thing the thing that changed is the maybe the additional functionalities have been added to the CPUs, like say some security features, some paging mechanism for memory management and all that. So, they have been added. As a result, the structure has become more complex, but essentially the access pattern or this design part, so that remain based on this 8086 processor only. So, that is the reason why we are looking into this 8086 processor. So, what we will do is that since we have already learnt 8085, so many a time, so we will be just referring to 8085 and trying to see that what is the new feature that we have here. Okay. So, start with 8086. So, this is the first 16-bit processor released by Intel in the year 1978, that is pretty old. So, first 16-bit processor. So, people thought that okay, instead of having this 8-bit processor which is very small, the capabilities may be less. So, why do not we go for 16-bit, so that our basic operations will be on 16-bit data. So, our operation will be faster and it is more powerful. So, and also you can accommodate more number of instructions. So, if you are having say 16-bit word size, then you can accommodate more number of instructions. Like 8-bit word size, so you can have only 2 power 8 different instructions possible, but with 16-bit you can have 2 power 16. So, that is if your opcode size is 16-bit, so you can have 2 power 16 different instructions possible. So, this was originally designed on HMOS technology, and now it is HMOS 3 technology is used. So, it uses approximately 29,000 transistors, 40 pin dual inline package and 5 volt supply voltage. Does not have internal clock and external asymmetric clock source with 33% duty cycle. So, you have to give clock from the external world, so from the external, and then it has got 33% duty cycle. So, it is so 1/3 of the clock duration it should be in high state, and the remaining time it should be in the low state. Then the address is 20-bit address. So, compared to 8086, 8085 that had 16-bit address. So, this has got 20-bit address, and naturally it can access 2 power 20, that is 1 megabyte of memory space, whereas 8085 had 16-bit address bus. So, it could access 2 power 16 or 64K address space, but this can access 2 power 20 or 1 megabyte of address space. And then addressable memory space is organized in 2 banks of 512 KB each. Okay, so, that is lower bank or even or lower bank, and odd or higher bank. So, address line A0 is used to select even bank, and control signal BHE bar is used to select the access the odd bank. So, we will see these control lines later. There is a separate 16-bit address for IO map devices, and naturally it can generate 2 power 16 kilobyte of as 2 power 16 is 64 kilobyte of addresses. So, in case of 8085, so you remember that this input output statement, so they were having only 8-bit address bus. So, you have 8-bit address can be specified there. So, you could connect only 2 power 8 or 256 devices, but here the address space for the IO is also 16-bit. So, you can have 2 power 16 different IO devices connected to the processor. So, total 64K addresses have been dedicated for the IO devices. So, they can be connected to that. It operates in 2 modes, minimum mode and maximum mode. So, there is a min max bar pin. So, this min max bar pin, so that will be deciding the operation of that. So, minimum mode means it will be in that mode, the most of the time the processor will work, and there the instruction set is restricted. Normally the user programs, they will be executing in the minimum mode, and sometimes when you need the system mode of operation with unrestricted access for every part of the processor, so you can use this maximum mode. So, that is the min max mode. So, pins and signals. So, we will be looking into different pins that we have, like 8086. So, it has got these pins AD0 through AD14. Then these are the 15-bit addresses, and then we have got this AD15 pin. So, that is also there. So, 16, 17, 18, 19. So, this is the 20-bit address bus, and you see that address bus is also multiplexed with data bus. Okay. So, this we have got 16-bit data bus AD0 through AD15, the D0 to D15, but also we have got some more lines. So, this this should better be treated, though the names are given as AD16, AD17 like that, but they are only address bus pins, and they are multiplexed with some more status pins S3, S4, S5, S6, and S3, S4, S5 and S6. So, these 4 status lines are multiplexed with this address bus. So, that is why none of the address bits are free. So, they are coming as 20-bit address and 16-bit data bus. Then other important pins that we have are say this we have got this lines like this non-maskable interrupt, then interrupt line. Okay. So, we will explain them one after the other. So, AD0 to AD15, so they are bidirectional bus. So, they are address and data bus. So, these are low order address bus. So, these are multiplexed with data. So, when the AD lines are used to transmit memory address, then this the symbol A is used instead of AD. So, we call it A0 to A15, and when they are used for transmitting the data, so we will use the line D0 to D7, D8 to D15 or D0 to D15. So, for IO device, so there will be D0 to the data bus lines will be there on a separate address line A0 to A15, and for memory access, so we have got 20-bit address. Out of that, these 16 bits are A0 to A15. Then A16, as I was telling that A16, A17, A18 and A19, they are the higher order address bus lines, and they are multiplexed with status signals. Okay. So, they are also multiplexed, but they are multiplexed with the status bits S3, S4, S5, S6. Then there are some interesting lines, this BHE. So, bus low active, so it is an active low signal. So, bus high enable or status. So, it is used to enable data onto the most significant half of the data bus, that is D8 to D15. So, if you are trying to get the value on D8 to D15, then this BHE line should be made 0, and 8-bit device connected to the upper half of the data bus use this BHE signal. So, it is multiplexed to the status line S7. So, this BHE signal for the lower order byte of the access. So, as I have said that the data bus is 16-bit. So, it may come from 2 8-bit locations. Okay. So, like if I have got 2 memory banks, then one memory bank may be activated by one signal, the lower memory bank may be activated by some signal, the higher memory bank is activated by this BHE signal. So, BHE signal should be low for activating the higher part of the data bus. Then this minimum maximum min max bar pin. So, this pin will indicates what mode the processor will operate in. There is a read signal which is active low. So, it is for read operation, output signal, and it is active when the output is low. This is this read bar line. So, for reading the value from the outside world. So, we have got this test line. So, this is again a active low line, this test bar line. So, this is an active low line. So, it is tested by the wait instruction. So, this is for connecting some output device. So, if the output device is asking the 8086 to wait, so it will be the 8086 program may execute an wait instruction, and then the instruction will the 8086 will be put into an wait state, and then where it will be sensing the line test bar. So, when this test bar line is activated, then only it will go to the 8086 will come back to its operation. So, it will be activated from that point onwards. So, this is used to synchronize an external activity to the processor's internal operation. Like there may be many devices in my system, and some device may be doing something at which this activation this 8086 program is also running, and maybe the program needs some data from some device, okay, then and that device may not be ready yet. So, so what the processor does, finding that it is not ready, it goes into an wait state, it executes a wait statement and goes to the wait state, and in that wait state it will wait for this test bar line to become low. So, when this external device is ready, so it may send this test bar line low. As a result, 8086 will come out of that wait state and it will be continuing with the next instruction. So, this is the test instruction test pin, and there is a ready pin. So, if the outside memory is slow, if the outside memory is slow, in that case the once the address bus has been getting the value of the address from where from which location we want to read the value, then the memory needs some time for getting that data onto the putting the data onto the data bus, but the processor may be faster than this memory. So, the processor has to wait, and for that purpose this ready signal is there. So, what the memory module can do, it can put this ready line low, so that it will be the processor will be waiting, and when this ready becomes high, that means the memory has completed the data transfer. So, that way it can be so now the processor can read the value. So, this way this ready signal can be utilized. So, this is also true for 8085 processor. So, there also we had the ready line. Then there is a reset pin. So, that will cause the processor to immediately terminate its present activity. So, it will be reset, and then it will be going back to a predefined value of the program counter. So, it will start executing from that point, and for the sake of security, or to make sure that the reset is really desired, it is not a noise signal, the signal must be active high for at least 4 clock cycles. So, if it is less than that, then the signal will not be taken as a valid one. So, it will be ignored, and if it is high for 4 clock cycles, then only the reset will take place. Then we have the clock signal. So, clock will be that provides a basic clocking basic timing feature for the processor and this bus control activity. So, it is an asymmetric square wave with 33% duty cycle. As I said, that the high time should be 0.33 of the total clock period, and low time will be 0.67 of the clock period. Then there is one interrupt request pin, INTR. So, this is same as similar to that INTR pin that we have got in 8085. So, this is a triggered input, and it is sampled on the last clock cycles of each instruction to determine the availability of the request. So, similar to 8085 again, that the interrupt line will be sampled on the last clock cycle. So, if on that clock cycle it finds that there is an interrupt that has come, then only this interrupt line will be sensed. Okay. Then if the interrupt is pending, then the processor will go into an interrupt acknowledge cycle, activating that INTA signal, and again the same thing, the device should put the address onto the data bus of this of the interrupt service routine, and from that point the interrupt service routine should start. So, these operations are similar to this operation of 8085. Then we have got this min max pin. So, min max pin, so this has got two modes of operation. 8086 processor, it can operate in minimum mode or in maximum mode. In minimum mode of operation, the microprocessor do not associate with any co-processors and cannot be used for multiprocessor system, whereas in maximum mode it can operate in the multiprocessor mode or the co-processor mode. So, in minimum or maximum mode can be activated by this min max bar line. When you are not using it with other processors, so you should put it in the deactivated mode. So, this min max line should be made equal to 1, because putting it on the maximum mode, so we have to put it as 0. So, this way we can go for this min max mode of operation. So, in minimum mode of operation it does not associate with any of the processors. Then in maximum mode it will work, it can work in a multiprocessor environment. So, you can put a number of processors and they will be cooperating with each other for doing some job done. So, that way you can put in a multiprocessor environment. Then activated by this min max bar line, and for minimum mode of operation, so you should put it in the minimum mode, otherwise high, you should put it at high for minimum mode and low for maximum mode. So, for minimum mode of operation, so this min max bar line it should be tied high, okay, this min max bar line, so it should be tied high. And then we have got these other lines like this 8086 will generate all the control signals for this operation, for the operation, because that is the only master for the bus that we have here in this mode. So, this DT R bar line, so this is for data transmit receive. So, this is the signal from processor coming out of the processor to control direction of data flow through the data transceiver. So, if you are transmitting the data, then it is data transmit, and you are receiving the data, it is receive bar. So, if this line is 0, it is basically that DR bar, that is data receive bar, and if it is transmitting, then DT equal to this. Then we have got this DEN bar, data enable bar line. So, output signal from the processor used to as output enable for the transceiver. So, DEN bar. So, if you are connecting some transceivers into this with this 8086 processor, so this DEN bar line can be connected to the corresponding enable line of this transceiver, so that it is activating as for output signal. Then we have got the ALE signal. So, this is address latch enable. So, for demultiplexing address and data lines by using external latches. So, this same as the 8085 we have the ALE line. Then there is M by IO. So, this M by IO bar. So, this is used to differentiate between memory access and IO access. So, just like 8085. So, for memory access instruction, this M IO bar line should be made high, and for instruction for IO access, this M IO bar line should be made low. Then there is a write bar line for write control. So, if you are putting it as low, then it will be doing a write operation. Okay. So, we are going to do a write operation, and then we have got this INTA bar line, that is the interrupt acknowledge. So, if you are asking for an interrupt, if you find that there is an interrupt at the end of the current instruction, then the processor will enter into the interrupt acknowledge cycle and do the operation. Then we have got two more pins, hold and hold acknowledge. So, which is similar to 8085 again. So, this is input signal to the processor, hold is an input signal to the processor, and that way it can request. So, the other bus masters that we have in the system, they can request for this holding. So, they can tell the 8086 processor to hold, and so that it to release the address and data bus controls, so that those devices they can take control of these pins of these address and data bus and do the operation. And there is a hold acknowledge. So, hold acknowledge will acknowledge it is an acknowledgement signal. So, that is given by the bus master to the controlling the 8086 processor to which this hold has come. So, when it is done with releasing the buses, okay, so it has released the control of this address and data bus, then this hold acknowledge line will be activated, so that the requesting processor or requesting master will know that now the buses are free for my use. The other 8086 processor, it has released the bus, so it is now for use by us. So, this hold acknowledge is an acknowledge signal by the processor to the bus master requesting the control of the bus through the hold pin. The acknowledge is asserted high when the processor accepts hold. Accepts hold means it has released the address and data bus controls. Then in the maximum mode of operation, so we have got these status signals like S0, S1, S0, S1 and S2. During maximum mode, this min max bar line is grounded, and this S0, S1, S2, so they are the status signals, and they are doing it like this. Then when it is 0, 0, 0, so this is an interrupt acknowledge cycle. 001, so this is read IO port, 010 is write IO port, 011 is halt. So these are different type of access. Then this part is interesting, like you see that this 100, 101 and 110. So these are three instructions, the three different status modes. So where it will try to differentiate between code access and data access. So if it is 100, that means it is doing that opcode fetch, 101 is reading from memory, and 110 is writing onto the memory, and 111 means the processor is not doing anything. So it is in the passive or inactive mode. Then there are two more pins, QS0 and QS1, which are known as Q status. The processor provides the status of Q in these lines. So this Q basically what happens is that 8086, if you look into the internal block diagram, you will find that there is a instruction queue. Instead of having a single instruction register, there is an instruction queue. So it is it can tell like how many instructions are there in the queue. The queue is by default 6 byte wide. So this is it can tell like what is the condition of the queue. So like say when it is 00, there is no operation. Then 01, the first byte of an opcode is from the queue. Then 10 is to empty, the queue is empty, and 11, the subsequent byte from the queue has to be read. So this queue status, the processor provides the status of queue on these lines. The queue status can be used by external device to track the internal status of the queue in 8086. So what is happening inside? So if you want to know at that instruction fetch, decode, execute cycles, so you can keep a watch on this QS0 bar and QS1 bar line. The outputs can be outputs are interpreted as shown in this table, that is no operation or first byte opcode from queue, so like that. Then we have got some more pins, RQ GT0 and RQ0 GT0 and RQ1 and GT1. So this is a bus request grant. So these requests are used by other local masters to force the processor to release the local bus at the end of the processor's current bus cycle. So in minimum mode of operation, so we have got hold, acknowledge. For maximum mode of operation, we have got this RQ GT lines. Okay, so there other processors can tell the 8086 that okay, you release the bus at the end of the current cycle. So that way these pins are useful. That these pins are bidirectional. So it can, like this processor can also send a request to another processor. That's why it has to be bidirectional, and it is also there is a priority, that is GT0 will have higher priority than GT1. So if there are requests on two different masters for this release of the bus, then this whichever is requesting on line 0, so that will be taken and that will be getting the bus. Then there is another line lock. So this is output signal activated by the lock prefix instruction. So you see that some instructions have got lock prefix, and this remains active until the completion of the instruction prefixed by lock. So this is basically the output will be made low while executing instruction prefixed by lock to prevent other bus masters from gaining control of the system bus. Like if some processor if the 8086 in maximum mode it is there, so we have got a number of such masters connected to the device, a number of 8086 chips. So each of them can act as a master. Now for some of the instructions, what can happen is that it is not possible to release the bus. So those instructions while executing, they will have a lock prefix in them, so that this lock signal will be activated, and then other processors, they will know that now the instructions that this particular processor is executing, it is in lock mode. So it will not release the bus. So even if I tell it, even if I send it a request to that RQ0 GT0 line that that I release the bus at the end of current instruction, so that will not happen. So that way this facility lock has been provided for locking the buses for the processor. Next we look into the architecture of this 8086 processor. So this is the architecture. You see that it can be broadly divided into two parts or two regions. One is called bus interface unit, another is called execution unit. So in the bus interface unit, we have got the features by which it can access the bus, the address bus and the data bus. So, this, as you know, that in case of 8086 we do not have two separate buses. So, it is multiplexed AD0 to AD15 or and then we have got this we have also got this status lines multiplexed with the bus. So, ultimately it is a 20-bit bus that is going out of 8086. Okay. So, this is the 20-bit bus. So, address 20-bit address bus is going, and out of that lower order 16 bits will be taken as data bus when it is doing the data operation, and there is a bus control logic. So, bus control logic from which this bus will come out. So, ultimately one bus is coming out of the 8086 processor. Unlike 8085, so there were two buses. One bus was a 16-bit address bus, and another bus and out of that 8 bits were for the higher order 8 bits were not multiplexed with anything, but the lower order 8 bits were multiplexed with the data bus. But here entire address bus and data bus, they are multiplexed, and ultimately you get a 20-bit bus from the processor. Then if you look into the address generation unit, you will see that there is an instruction queue. So, in case of 8085, when this bus when the data bus was coming inside the processor, from there it was going to some instruction register followed by decoder. But here it does not happen like that. The instruction register has been replaced by a 6-byte queue, so that we can have 6 different bytes loaded. So, depending upon the instruction size, so these 6 bytes may constitute a single instruction, or they may constitute say 6 different instructions. So, both the extents are possible. So, whatever it is, so whenever this external bus is free, 8086 will request the memory to get the next instruction from there and put it onto the instruction queue. And of course, if some instruction is a jump or branch type of instruction or call type of instruction, then it will ignore the content of current queue. So, it will flush out the queue and it will start loading from the new location afresh. So, that way this queue is handled. So, it will be getting the instructions from this bus and put onto this queue. Plus, there is a set of registers which are known as segment registers, CS, DS, ES and SS. So, they are called, the CS stands for code segment register, DS stands for data segment register, SS stands for stack segment register, ES is called extra segment register, and there is one instruction pointer IP. So, each of these registers, they are 16-bit registers, and these 16-bit registers and so one of these 16-bit registers and this IP value. So, they are put onto this address generation unit. Accordingly, it generates a 20-bit address from these to 16-bit data. It generates a 20-bit address, and this 20-bit address goes to this 8086 bus to the outside world as the address bus. And sometimes we also need to connect to this data bus is also connected here, because we may need to do some operation on the data that is coming from the data bus. So, some computation related to the address. So, that is why it is connected there. Otherwise, this instruction queue, so from this instruction queue, so the instructions, they come to the internal control systems, the other part of this architecture, which is the execution unit. So, in the execution unit, so it will be having a number of general purpose registers AX, BX, CX, DX, each of which is basically consisting of two 8-bit registers. For example, AX consists of AH and AL, BX consists of BH and BL, CH consists of CH and CL. So, like that it consists of a number of registers. And then we have got this SP, BP, SI and DI. So, those registers, so they will be consisting of they are some special registers for doing the purpose. So, other control unit, other portions that we have in this portion of this execution unit. So, there is an ALU, this ALU is doing the actual operation, some temporary registers for doing some holding some temporary data, flag register just like that PSW register we have in 8085. So, here also you have got flag register, and that way this whole control takes place.